So this is section 10.5. All right, I want to start with a couple of reminders. So for a regular polygon, the area is the apothem times the perimeter divided by 2 square units. This always works. For regular polygons. We can use special right triangles only for hexagons, equilateral triangles, and squares. If we have a regular polygon that is not a regular hexagon, an equilateral triangle, or a square, Sohcahtoa always works for right triangles. So we saw the other day how we can draw a little triangle in a regular polygon. We can figure out the central angle. So we can figure out an angle in that triangle. And then we can use Sohcahtoa on the little triangle that we draw to find missing pieces if we don't have a regular hexagon, an equilateral triangle, or a square. So we can use what we know about Sohcahtoa to figure out these missing pieces. So what I want to do is go through a couple of examples of applying this to a regular polygon that's not a hexagon. And then the last thing we'll talk about today, we're going to come up with or we'll write down a new area formula for the area of a triangle. We can use trigonometry to help us find the area of a triangle. All right, so let's look at an example. This is a regular octagon. I'm going to draw a picture here. It's not, my octagons don't turn out perfect, so just bear with me. Not a terrible octagon, but it's definitely not a perfect regular octagon. And I'm going to say the side length is 7.5 inches. And we want to find the area. Well, it's not a regular hexagon, so we can't use special right triangles. To find the area, we need the apothem. So we need to plug that into, we need the apothem to find our area. Well, let's draw this little triangle here. Here's my center. There's the apothem. And I drew in a radius also. Well, what does the apothem do to this side of the polygon? Cuts it in half. So this is half a side. And we also talked about the central angle. This angle in the triangle is half a central angle. So we can figure out a side of this triangle. Half a side is 7.5 divided by 2, which is 3.75. And half a central angle, well, the central angle is 360 divided by 8. For any regular polygon, the central angle is 360 divided by the number of sides. Well, 360 divided by 8 is 45 degrees. So half the central angle is 45 divided by 2, which is 22.5 degrees. So I'm going to redraw that little triangle. Just make it a little bigger here. So there's a triangle that I have. Nice right triangle. This is 3.75. This is 22.5. And we need the apothem. Well, we have a right triangle. We know that Sohcahtoa always works. So let's label this triangle. Is, for the 22.5, is this the opposite, the adjacent, or the hypotenuse? That's the opposite side. How about the apothem? Adjacent or hypotenuse? That's the adjacent side. So then we go to Sohcahtoa and we say, well, what trig ratio tells us about the opposite and the adjacent? Let's write it up here so it would be Toa, so it's tangent. So we're going to use tangent. So we're going to say the tangent of the angle, 22.5 degrees, is the opposite, 3.75, over the adjacent, which is the apothem. This is the kind where we have to be a little careful about solving this. Multiply everything by a, so those go away. I get a tangent 22.5 degrees equals 3.75. And then I divide everything by tangent 22.5 degrees. So those go away. And I get the apothem is 3.75 divided by the tangent of 22.5 degrees. Plug that in my calculator, and I get the apothem is 9.05. We also need to plug in the perimeter into our equation. Well, the perimeter is going to be, the side length is 7.5 times 8. 7.5 times 8 is 60. So my area is the apothem, 9.05 times the perimeter, 60, divided by 2. Plug that in my calculator, and I get that the area is 271.5 inches squared. Just checking my units. So we were able to use Sohcahtoa on the triangle here to find the apothem. All right, questions there? All right, I want to do one more example where we have a slightly different setup. This one is going to be a regular pentagon. So here's a regular pentagon. That's right. And I'm going to draw in this piece. And we'll say that that is 9 inches. And we want to find the area. Well, it's not a regular hexagon, so we can't use 30, 60, 90 triangles. We need the apothem and the side. So I'm going to draw in the apothem. We know that gives me, cuts that side in half. So I'm going to call that A, and I call that X. So we need the apothem and the side. Well, we can use this triangle to find the apothem and the side. we can find the angle in the triangle. We know is a central angle divided by 2. The central angle is 360 divided by 5, which is 360 divided by 5 is 72 degrees. So the angle in the triangle, 72 divided by 2, which is 36 degrees. So I'm going to put that in there in the triangle, 36 degrees. Well, now we can use this triangle with Sohcahtoa to find both of those pieces. So let's label this little triangle. Is this 9-inch side the opposite, the adjacent, or the hypotenuse? That's the hypotenuse. This apothem, opposite or adjacent? That's going to be the adjacent side. So this is the opposite side. Let's find the apothem first. So for the apothem, we're looking at the adjacent and the hypotenuse. Which trig ratio tells us about the adjacent and the hypotenuse? Cosine. So I'm going to say the cosine of 36 is a over 9. Multiply both sides by 9. And a equals 9 cosine 36, which gives me 7.28. For x, I'm looking at the opposite and the hypotenuse. What trig ratio tells me about the opposite and the hypotenuse? I can write it up here. Sine. So I'm going to say that the sine of 36 degrees is x over 9. So same thing we did before, multiply both sides by 9. And x equals 9 sine 36. And I plug that in my calculator and I get 5.29. So the side of the pentagon is 5.29 times 2, because we found half a side, so we get 10.58. The perimeter, 10.58, we have a pentagon, so times 5, and that gives me 52.9. And now we can find our area. The area is the apothem, 7.28 times the perimeter, 52.9, divided by 2. Plug that in my calculator, and I get 192.6 square inches, rounded to the 10. So for this particular problem, because we have the radius, we use Sohcahtoa to find the side length and to find the apothem. All right, questions? All right, the last thing for today, a new area formula. Area of an SAS triangle. So if we have a triangle, we'll label it like we did when we were talking about trigonometry before, with capital letters for our angles and small letters for the sides across from the angles. The area of this triangle equals side B times side C times the sine of angle A divided by 2. And what we're looking at is those two sides and that angle. We have two sides plus the included angle. So we have a side, angle, side triangle. This formula comes from the law of sines. That's why it kind of looks, the one white has a sign in it. And it kind of looks like it might have something to do with law of sines. So our formula comes from law of sines. Nice thing about this formula, it's really easy to use. So if we have a triangle and we know two sides and an angle, we can find the area very easily. If I know that's 36 degrees, that's 8 centimeters, and that's 12 centimeters, and we want to find the area, I can label it if I want, so it matches up with my formula. I can call this angle A, so this would be B and this would be C. The area would be 12 times 8 times the sine of 36 divided by 2. Plug that in my calculator. I put parentheses around all of this when I put it in my calculator. Plug that in, and you get 28.2 square centimeters. That's all there is to it. Plug those numbers in, and you're set. And here we have the two sides and the angle that's between them. So we have a side, angle, side triangle. All right, questions? Okay. Homework?